Hello students, welcome to Adi Chemistry's online classes. I am Adityavardhan, the creator of adichemistry.com Warangal. In this presentation, I will explore Beer-Lambert's law, a fundamental concept in spectroscopy and an essential tool in analytical chemistry for quantifying the concentration of unknown substances and understanding their interaction with light. We know that when a monochromatic light passes through a solution, part of it is absorbed and the rest is transmitted. And according to Beer-Lambert's law, the absorbance A of the light in a solution happens in linear manner and is directly proportional to the concentration of the solution C, and the path length L of the light through the solution, which corresponds to the length of the container holding the solution. The concentration is typically given in molarity and the path length is measured in centimeters. We can express this relationship mathematically as A is equal to epsilon multiplied by concentration and the path length. Here the epsilon represents the molar extinction coefficient or molar absorptivity. The molar extinction coefficient epsilon is a measure of the amount of light absorbed per unit concentration at a specific wavelength. It is an intrinsic property of the compound. This value differs for every compound. It is expressed in units of per molar per centimeter or liter per mole per centimeter. While expressing the molar extinction coefficient of a compound, we have to mention the wavelength of the monochromatic light also. When absorbance A is plotted against concentration C, the graph is a straight line that passes through the origin. The slope of this line gives the molar absorptivity epsilon when path length L is known. The absorbance A represents the fraction of light absorbed by the sample, while transmittance T refers to the fraction of light that passes through the sample without being absorbed. Both absorbance and transmittance are expressed as decimal values between 0 and 1. Both are dimensionless. These two are inversely related. As absorbance increases, transmittance decreases. Mathematically, absorbance A is the decimal logarithm of 1 by t or the negative logarithm of t to the base 10. Transmittance T can be defined as a ratio of transmitted light intensity I to the incident light intensity I naught. Thus, absorbance A can also be written as negative logarithm of I by I naught or logarithm of I naught divided by I. Transmittance can also be expressed as a percentage known as percentage transmittance %T. This is calculated as %T is equal to T multiplied by 100. Therefore, the absorbance can be rewritten as A is equal to negative logarithm of %T divided by 100 or 2 minus log %T to the base 10. The Beer-Lambert's law is used in the determination of concentration of solutions. It has applications in UV visible spectroscopy. It is also used in pharmaceutical industries. It is used to measure the drug concentrations in various formulations. Let us now see what are the limitations of Beer-Lambert's law. It is valid only for dilute solutions. There should be no chemical change of sample in the solutions. There should be no scattering of light, and there should be no fluorescence or phosphorescence. Now let us work out a problem based on Beer-Lambert's law. What is the concentration of a solution whose absorbance is 0.21 when placed in a tube of path length 10 centimeters? Here lambda maximum is given as 245 nanometers and epsilon is given as 31,500 per molar per centimeter. So from Beer-Lambert's law, the concentration is given by absorbance divided by epsilon and the path length L. It works out to be 6.67 into 10 power minus 7 molar. This is the concentration of the solution. That's all for now. Visit adichemistry.com for more information on this topic. You can also find links to worksheets and other study material in the description section. If you find it difficult to reach them, don't hesitate to ask me in the comments section or drop an email to adichemadi@gmail.com. Okay, all the best. Don't forget to like, share, and subscribe.